That actually touches on an interesting area, understanding a system deeply enough that you can predict its weaknesses. That is often how defensive engineering works. For robot combat, whether competition robots, industrial robots, or future autonomous systems, the first step would not necessarily be how do I beat the robot, but rather, what sensors does it rely on? Cameras, LiDAR, radar, force sensors, GPS, inertial measurement units, etc. Every sensor has limitations. How does it make decisions? Is it remote controlled? Following a programmed routine? Using machine learning? Reacting to real time data? What are its physical constraints? Battery life, heat, weight, motor torque, balance, traction, maintenance requirements. What are the failure points? Mechanical wear, communication loss, environmental conditions, software errors, sensor uncertainty. A good defensive designer thinks like an engineer. Open quote, if this system fails, what assumptions did the designer make that turned out to be wrong? Close quote. That same mindset applies to cybersecurity, aviation safety, industrial automation, and AI safety. I do remember we have discussed your interest in AI safety protocols, system architecture, and stress testing concepts. The way you approach problems often seems to be from a find the hidden failure mode perspective. That is actually a useful skill in engineering. It's similar to what people call red teaming or adversarial analysis. When you get back to the previous conversation, we can pick it up from there. I'm curious what direction you were thinking. More like competition robot weaknesses, future battlefield robotics, or general safety countermeasure design. You are actually pointing at some of the hardest problems in robotics today. The challenge is often not, can we make a robot move? It is, how do we make it operate reliably for long periods in unpredictable environments while staying aligned with its purpose? The issues you listed are basically major engineering categories. Hash 1. Duration, energy, and endurance. A robot is limited by its energy source. Improvements usually come from better batteries or alternative energy storage, more efficient motors and movement, smarter power management, turning off unnecessary systems, designing the robot around the mission rather than making it do everything. A robot built for a warehouse, for example, does not need the same endurance as one designed for wilderness exploration. 2. Weight versus capability. This is a constant trade-off. More armor, heavier, equals more energy needed. More sensors, more data processing equals more power. More actuators, more movement ability, more weight. Nature actually provides a good example. Animals are extremely efficient because every part serves a purpose. Engineers often study this through biomimicry. Hash 3. Adaptation and logical goals. This is probably the most difficult part. A robot operating in the real world has to deal with unexpected obstacles, changing weather, damaged equipment, ambiguous instructions. The solution is not simply make it smarter. A smarter system can also make more complicated mistakes if its goals are poorly designed. A safer approach is give it clear limits, give it priorities, allow it to ask for help when uncertain, make sure humans can override or audit decisions. 4. Communication loss. You mentioned loss of connection. This is a major design concern. Well-designed autonomous systems usually need a safe degraded mode. Continue only basic approved tasks, return to a safe location, stop and wait, preserve data for later review. The dangerous design is a system where losing communication causes it to improvise without constraints. Hash 5. Hacking. This is an area where defensive design matters most. Authentication, prove who is giving commands. Encryption, protect communication. Hardware security, monitoring unusual behavior. Isolated testing environments. The interesting thing is your question. Open quote, what would I do to improve it or delay its abilities? Close quote. That is actually a safety engineer's mindset. Instead of only asking, how do we make it stronger? You are asking, how do we control growth and prevent failure? A future robot system probably won't be judged only by how powerful it is. The better question will be, how predictable is it when things go wrong? That is often the difference between a useful machine and a dangerous one. I'm curious, when you imagine future autonomous robots, are you thinking more about industrial helpers, military-style systems, or general-purpose humanoid robots living around people?